Hello again, folks, in 114. Today we're going to be starting a new chapter, chapter 7, so we'll be covering section 7.1. Here's the calendar. Let's see, today is Monday, June 7th, so we'll be covering section 7.1. Okay, very good. Still on schedule, right? The packet that I have for you looks like this. There's a diagram that I left blank here and here and here because I want to fill this in with you. And then there is something that I copied from an old notebook, the inside cover, a list of conversion factors, basically. These are not going to be immediately important, but this is just part of the conversation, for the sake of comparison, really. Then there is a second diagram I made. This is an overview, basically, of chapter 7, section 7.1 to 7.3. But again, I kind of left some of it blank because it's not pertinent right now. But I'll annotate that. Then there's this, which is how you might think about converting in metric units, and an alternative which is actually more efficient. I'm going to show you both ways to do this. And then there's some summaries and diagrams that I swiped from the book for reference. And we'll go through some examples. I left the solutions for these just in case you were not watching. You can figure that out. Okay. Alright, so I'm going to put that aside. And I'll turn on my projector here and adjust the lights. Remember, if you want, maybe just to separate out in your notes where chapter 6 and chapter 7 interface, just fold over a page, corners to the center, make a little border. It's anticipated to be rather hot today. Expected to be. Yeah, right. Something mess with my camera. My glasses. Let's see. Okay. Let me start with this. In the United States, there are actually two systems of measurement. All right, there's what is really elsewhere referred to as the imperial system. I guess it's just being stubborn children that we are. We prefer to call it the customary system here, but it is nonetheless the imperial system because we were once a colony of the British Empire. But then there's the metric system, and that's how we refer to it. Oftentimes, if you're in a science course, you will see this exclusively referred to as SI units. All right. I forgive my pronunciation. Système International des Unis, I believe is how you pronounce it. The International System of Units. Again, SI is how we tend to refer to it here, with the metric system. Interestingly, the imperial system is actually, parts of it are ancient, you know. For example, something like this. I'm sure I'll go with black just to save myself some trouble. An example of the imperial units that we still use here are, forgive my allergies, miles, for example. The Romans had a mile. It isn't defined exactly the same way, but the concept of a mile goes back at least to the point of Roman times. This was, I would say, vaguely 1,000 paces, however wide a pace is. Let's get the dud. Somebody's stride might be a little bit wider than, say, somebody else's, but approximately 1,000 paces. Nowadays, we have this more clearly defined. Officially in the United States, a mile is 5,280 feet, or you might say 1,760 yards. Okay. Let's see. The metric system, on the other hand, is something that you will see, even hidden in a way in the United States. It's unfortunate, but it's used in sciences and in engineering, and also in what you might call world market goods. I think these are drying out too. World market goods, which perhaps the color red is appropriate, because the example I want to show you is Coca-Cola. Coca-Cola is famously offered in liters. Right? I'm spelling it also fluid ounces, but why liters? Because virtually everywhere else on Earth, liters is the unit of volume. Right? I'm spelling it the American way, forgive me. When in America, do as the Americans do. E-R as opposed to R-E. Okay. Anyhow, the imperial system, again, parts of it at least come back from the ancient times, whereas the metric system is wee babe, starting from maybe 1790, about the time of the French Revolution. If there was one good thing that came as a result, right, it is the standardization of units. A universal system is very practical. Not to corrupt your opinion, but what is troubling about the imperial system is that it's less efficient, really. Right. And I would say that because it requires memorization. Of many conversion factors. And they would seem somewhat arbitrary. This is I'll put both of those away. What I have for you is, I won't turn off my camera, but I included this packet to emphasize this point. In any marble notebook that you purchase in the United States, if you look at the inside cover, there is the good old times tables. But there's often a lot of these conversion factors. They don't call them that, but that is really what they are. They might call them conversion tables, So for example, here's the metric units that they had taken the time to convert. All right. And here's the imperial system. Let's see, where is it down here? I'm reading it backwards, sorry. Here is a better example. 12 inches is 1 foot, 3 feet is 1 yard, 6.5 feet is 1 rod, which is a very uncommon unit here. 660 feet is 1 furlong, even less common. The mile is something that we use. Anyhow, there's quite an array of very different, inconsistent, you might say, conversion factors. Right? Whereas in the metric system, everything is decimal. Right? So it's much more predictable, even if you don't have the information memorized. And I would say, therefore, that this is more efficient for that reason. Basically, one can convert nearly by moving a decimal point. That is the same as dividing by powers of 10. Remember, when you multiply by 10, you move your decimal to the right. When you divide by 10, you move your decimal to the left. Right? As long as you know that that is what it is entailed, what is involved, then that is as hard, that's the level of difficulty of converting. It's just moving a decimal point, really, and you don't have to memorize a lot. So I hope I'm selling it. It's way overdue. All right, the rest of the planet, or much of the rest of the planet, basically use the metric system. America is slow to adapt in this regard. Okay, there is a diagram actually, which I will take the time to show you. Be prepared as a teacher in the United States of being met with some resistance. Some older people may resent, unfortunately, what seems to be an unnecessary change. And one could argue it isn't necessary to switch a system of units, but this is not something I would talk a child out of learning. You want to convince them that it's practical. Right? Just like having a common language, namely mathematics, is very practical. So would be having a system that is universally understood. Just to show you, here's an interesting table. This is called Years of Official Metrification, right, by country. Not all countries, of course, but quite a few of them, and the date. It's a bit bright because of the sun is coming in early this morning. 1795, you have it where it originates from France. Belgium and Netherlands in the 1820s. Colombia and Morocco, 1853. Brazil and Mexico, 1862. Germany, 1872. They became a country at that point. Around then. Let's see. Russia and China, 1925. Japan, 1957. Ethiopia and Nigeria, 1962. The UK, 1965 looks like. And Jamaica, according to this, was the last, 1998. I believe there might be some more recent country. Who is not on this list? At least at the time of the publishing of this particular textbook, which is maybe 2 or 3 years ago, the United States, Liberia, and Myanmar. All right, formerly known as Burma, as they would say. All right. And again, a system of units, if you have one, is fine. All right, but it would be good strategically in the long run to finally get on board. So that it's a little bit easier to convert things. All right, it's just more practical. All right, it's also good for science and engineering, which is very important. All right, now back to this. Here's that table I mentioned. I had it not projected yet. A lot of this, as you can see, is seemingly arbitrary. Some of it's misleading, right? Like, for example, the time measurements that we have go back to the Babylonian period. Remember that conversation, right? 60 is a number that they arrived at because of basically their hands. Now we think as a number system, as a basis derived from hands, we think of 10 naturally, right? but the Babylonians didn't just see 10, they saw 60, right? Because they didn't just count the fingertips, they counted the segments of the fingers, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all right? Times 1, times 2, times 3, times 4, times 5. 12 times 5 is 60, which is why it is, that number shows up, all right? Here are the units used for cooking. All right. I had to memorize this myself when I was a kid, and I kind of have a fondness for it, even now. All right. But as you can see, this is a little bit more cumbersome, right? You'd be hard pressed, probably in the United States and maybe anywhere, to have a very metric system for cooking per se, because it's considered something more of an art than a science. But if you worked for a company that they manufacture baked goods or what have you, all right, and you're trying to calculate, calorie count or joules, I don't know if they use this. 2 pints is 1 quart, 8 quarts is 1 peck, 4 pecks is 1 bushel. This is very old-fashioned, right? How often do you have the conversation of pecks and bushels with anyone, right? A cord, I think of chopped wood, In the winter, sometimes you see a sign around here that says, hey, buy a cord of wood for such and such price. And then it can get confusing because there are, say, for example, ounces when we talk about weight in the United States versus fluid ounces, which is a measurement for volume, right? So unfortunately, there is quite a lot here to assimilate, if you're going to really know your stuff. Not a bad thing to do, more is always better. But we want to encourage some consistency. So, especially in education, Now, let's discuss this. The metric units that you're going to see, and I'm sure that you probably have already, are for different physical measurements. There's measurements of distance, right? Measurements of capacity, of mass, which is proportional to weight, but they're not the same thing, and temperature, of course. Right? The way that it's chopped up in our book, and this is the subject for today, this is section 7.1, so we're going to really just be covering distance. Let me move this up just a little bit before I set myself up for failure here. And I'll back this off a wee bit. This is section 7.1, and that really is the subject for today. Introducing metrics and specifically for length, distances. Capacity, which is volume, is section 7.2. I'm going to just merely touch upon this for a moment. But these two, mass and temperature, they are section 7.3. And what will occur eventually is converting between the imperial system and the metric system in section 7.4. Okay, but we need to introduce these different types of physical measurements first. Okay, now, what is called the base unit, right, of distance, take it for granted, is the meter. Right? The meter is approximately, I have a rule here, so perhaps I can show you. This is a T-square, like my father used to have. And it's for, cutting sheetrock. But anyhow, if you were to measure from here, say 0, right, to approximately, where is that? There, a little bit hard to see, this distance from here, look like I'm holding a guitar, right? This is 36 inches, that would be a yard. A meter would be approximately 39 inches, but it's rounded, of course. So it'd be just a smidgen longer. Right? Anyhow, one could convert, and that is again the subject of section 7.4. The base unit for distances essentially is the meter. All right, now bear in mind, distance is a one-dimensional measurement, right? And it has a slew of different names, right? You could, when you're talking about shapes, for example, you could refer to the side of the shape, even though a shape itself is minimally, two-dimensional. Any one of the sides that enclose the shape would be referred to as a side. You could, if you want to, say in the case of something like a rectangle, be a little slightly more specific, and instead of referring to something generally as a side or a distance, you could refer to it as a length. And then to distinguish it from other sides, called the second thing a width. And then in theory, if you have something that is three-dimensional, you might make it a third dimension that is still one-dimensional each, a height, right, or a depth. It's usually these three labels that are considered when we're talking about something that's a volume, right? And that again is a capacity, right? Capacity is three-dimensional, distances are just individually one-dimensional, right? When you zero in on the unit, the abbreviation, although people tend not to do this, is they'll use M for meter. In other words, the thing was measured in meters, whatever it is. And then it would be exponents of 1. Right? Ones are optional, they don't get written too often. But if you want to be ultra clear, you could make that information known. Slightly smaller font in superscript. When you calculate a volume, you're really just multiplying these things. And in that instance, the exponents get added. So this is why if you see, for whatever reason, a volume of a solid as opposed to a volume of a liquid, the science engineering community has basically decided that we'll use meters for solids, right? We'll use liters, cubic meters for solids, and we'll use liters for liquids, or gases a lot of times. Anyhow, for right now, just go distances, one-dimensional, capacities, otherwise known as volumes, three-dimensional, but we're not going to get there today, okay? Section 7.3 will cover these. Right. Now, as for notation and such, do beware, as an American, all right, globally, the metric system uses a comma in the same way that we use a decimal point, and vice versa. So, for example, if in the U.S., if I use something dark enough to see, if in the U.S. you see a number like 3.5, this is understood as being 3, and the decimal point is right as end, 5/10, as the 5 is sitting in the tenths place. All right. What you would, how it would be written elsewhere would be like so: 3,5. All right. Again, we use a decimal when we separate out whole numbers from fractions. All right. Elsewhere, they'll maybe use a comma. And vice versa. So if you had a much larger number, say for example you had 3,644,700,000, we would, if we bothered at all, we would put a decimal point here, again, because that's a whole number, a very large whole number. Group things in sets of 3, and typically put a comma every 3 like so. Whereas, again, elsewhere, you'll see the same number, 3,644,700,000, but you'll see decimal points every group of 3, like that. And technically, you could put a comma there. Right? So just make that distinction, right? Or be mindful of that if you're reading a sign from elsewhere. Right. We use periods, decimal points to separate out whole numbers from what are essentially fraction decimals, 5/10ths or what have you. And we use commas to group sets of 3. Interestingly, in the United States also, as a historical reference here, when it comes to the other side of the decimal point, we don't use commas anymore. What we were taught at least years ago is to group things still in sets of 3, but leave an obvious gap like this. So if there was any portion of this a decimal, to make it easier to read, there would be an obvious space here and here in every 3. I've noticed that some textbooks are a little lax in that regard, and they don't do that anymore, but hey, whatever. Just be aware. Let's see, what else is there? Another thing, you might notice that the etiquette in this textbook, or anything you do in my lab, is that when you have a 3-digit wide number, 3 and 4-digit wide numbers, there is no spaces. There are no spaces. No commas or spaces. So for example, if you have a number like, embedded etiquette would be something like this. $4,000, 4,00, something like that. A comma here, and then a decimal there. What you're inclined to see in this book, and in probably the examples, is just to write it like this. All right, for numbers that are, basically 4 digits wide. Okay, so just be aware of that. I guess it's arguably, it's stylistic, it kind of has an aesthetic to it, right? I hate that, unfortunately, only for the reason that, in math, we really should be less concerned with the way things look and more concerned with consistency. Anyhow, this is the way the book writes things, which is equal to that. Okay, not to belabor the point. All right, so you see where we're going and where eventually, or where we are and where we're going, all right? We're covering just distances today, so we're going to be talking about meters a lot. All right. Now, let me show you a table of my own invention here. Well, this is a derivative of the way I was taught myself, and I like it for certain advantages. Show you this. Firstly, it's entitled the metric system, of course. There are these spaces that are empty, purposely like a ladder, where you could write the base units and then the prefixes above and below. Right? You don't have to use this system, but the advantage to it is that you get acclimated to the abbreviations and the name of the prefixes. So let's start with this. The base units, of the metric system, again, depending upon whether you're measuring distances or capacities or so forth. Or I'm going to put a little hyphen here. Meter, and again, I'm spelling, forgive me, this is the American way, ER as opposed to RE. Abbreviated lowercase m, right? The liter, which historically is abbreviated capital L. Your book might use a strict L. And the gram. Or mass, which is abbreviated lowercase g. All right. attached to these, and it's the purpose for the hyphen here, is that you can convert the unit into a larger size unit or a smaller size unit. So what I would like you to do, if you're following along and you happen to have this sheet, is attach the prefixes of the slightly larger or increasingly larger units and the increasingly smaller units. So just above meters, all right, there is famously deca, which somewhat inconsistently is DK and some, or DA, dat, or just capital D, and then above that is hecto, H, and then above that is kilo, K. Right. Below a meter would be a deci unit. That's just D, lowercase d. Centi, which in the United States we are well familiar with centimeters. Any ruler that you have here has inches on one side and centimeters and millimeters on the opposite side. Below that is millimeters, which is coincidentally a lowercase m for the abbreviation. Right? Now, for the most part, this is really what the range in which you convert units, but there are other spaces above this. All right, I left blank because, especially as computer memory increases in capacity, you'll start to hear of megabytes and beyond megabytes, giga and tera. 3 spaces up, I put little bullet points here for this reason. 3 spaces up from kilo, on to the third one, would be mega, which is abbreviated capital M, if you're curious. And then another 3 up would be giga, which is G, and another 3 up would be tera. On this end, the down end here is below milli, 3 spaces is micro. And depending again on the author of the book, they might put MC for micro, or any science book that I've ever seen, they use the Greek mu, sort of a stylized U symbol. Right. Another 3 down would be nano, which is lowercase n. Right. Anyhow, this is a good exercise, I believe, as a teacher, because getting your students to write something will help them assimilate. They'll remember more, likely. If you're curious, in the packet, for the portion of it that is entitled Summaries and Diagrams, I made sure to include this table, right? As you can see, the prefixes, right? I stopped here at giga, right? There's tera and peta and exa, zeta and iota. And on the low end here, micro, nano, pico, femto, atto, zepto, yocto, right? And the equivalent of these is, let's see, in powers of 10, because you're talking about a decimal system, so base 10 is 10 to the first, 10 to the second, 10 to the negative third, and so forth. Okay, we have labels basically from the range of 10 to the 24th to 10 to the negative 24th. So that figure, right, versus that figure. Kind of a nice sort of pattern here, like an hourglass. All right. Anyhow, it's very good to, it's very important, I should say, to memorize these prefixes and the base units, right? At least in this spectrum from milli to kilo, right? That's very practical. right? If you get into a science course, especially biology, you'd be million to micro most likely. Right? And in chemistry and physics, nano scale, or very, very astronomically large things. You know? Anyway, the way that I was taught, and again, I just want to show you, because I think it's convenient. I'm going to erase this just for the space. It's convenient for memorizing these attachments here: decameter, hectometer, kiloliter, so forth. If you go from what is a smaller unit something that would be on the low end of the scale, up to a larger unit. Right? Essentially, you move the decimal point left. Right? That many jumps. Right? If you go from a larger unit down to a smaller unit, you move your the decimal point towards the right. Right. Again, the whole practicality of it having it stacked like this is just to get you used to these abbreviations. Perhaps you know them already, but this is the appropriate order that you must know them. Once you have that, what you can do, which is a lot more efficient probably, is draw the scale in abbreviations more or less horizontally. So let me just show you that now. This is a little bit more practical, the horizontal scale versus the vertical scale, because it tells you immediately what the direction is that you're moving a decimal point. You just have to label it correctly. You really must know the abbreviations and the base units and what they called and the prefixes. So let's talk about meters. Right? If meter is the base unit, then that should be in the middle. Right? To the right side of it would be decimeter, so I'm going to abbreviate that DM, and then centimeter, cm, and then millimeter, mm, and decameter, dm, hectometer, and kilometer. So essentially, if you are given something, you're going to put a dot on the scale for the unit that you are given. And then, depending upon what you're converting to, you will make jumps to that place. You know? So you may start here potentially, and you may end here. And this tells you 3 jumps. So you move your decimal 3 spaces that way to convert. It's a way of basically circumventing having to divide by, or even think about powers of 10 at all. Or if you're going the other way, multiplying. Okay? So let's do some examples now. It's getting a wee bit hot now because it's approaching noon. I'll draw this table several times. But let me turn off the projector for a moment, and then we'll continue. Lines here. Let me just sort of give myself a little space to work here. Each one of these is going to be, we'll just be converting between metric units. an example. Here's an example. Suppose you are given this 457.3 meters, the abbreviation, and you'd like to know how many kilometers that is. All right, what I would again encourage you to do is, if you're not familiar, just draw a number line. Right? The middle is the base unit of meter, which coincidentally is the thing that is given. And then you would have 3 increments this way: decimeters, centimeters, and millimeters, and decameters, dm, hm, hectometers, and kilometers over here. Now, again, depending upon what you are given is where you start on the scale. So you would put a dot here, right? This is where you're going. So what you want, you just have to draw leaps, basically jumps to that abbreviation from where you start. So if here's meters and km is over here, you would make 3 leaps this way. Right? 3 jumps. Alright, you essentially will move the decimal point 3 spaces left. It's that direction. Again, the horizontal scale is more intuitive in terms of where you're going to put your decimal point. Alright, that means that when you take your number up here, alright, you're just going to emulate that process. 457.3. Move, make waves, 1, 2, 3. And just to distinguish the decimal point from where it was to where it is now, I'm going to exaggerate this. Right? How to write it a little bit cleaner. All right, the end result would be this: 0.4573 kilometers. If you want, stylistically, you can put a little 0 here. Sometimes the book does them. But if you really want to get fancy, you could say 4,573 10,000ths, right? You will find, especially in a chemistry setting, people don't use the ultra fancy way of referring to a place as THS, right? Tenths, hundredths, thousandths, 10,000ths. But you could. More likely, and this is, I think, more practical, that we'll just simply read it as 0.4573. Right. Now, what drives people who have never seen this before a little cuckoo is they will go, hey, this is such a tiny number, as it's less than a whole number, right? Compared to this figure that it was, right? But the essence of what is going on here is that you have converted between metric units. You're using the mid-size unit, which is about that wide, and you've converted that amount to the larger unit, right, which is a kilometer. That's synonymous almost with miles, right? I think kilometers might be a bit longer. All right, I forget offhand. Anyhow, that is the reason for this being of a magnitude visually and misleadingly, as if it was somehow diminished. All right, it's not. This is still representing the same distance. This is still representing the same distance. It's just choosing to express that distance in a much larger unit. That's why it's 0.4 versus 400, on that magnitude. All right. Here's another one. Just to get you used to it. Uh, 14G and we want to convert that to so much CG. I don't see that unit too much, but one could, in theory, convert from grams to what would be centigrams. All right, more likely milligrams, right? That's just for practical purposes. Milligram being like the the amount of a vitamin. So here's the scale. All right, grams, just coincidentally, what we're starting from is the base unit. So G would go right smack in the middle. And then immediately to the right of it would be decigrams, a less common unit, centigrams, a less common unit, and then milligrams, which is quite common, right? Any time you go into the vitamin store, GNC, right, what do you see? You see, supplements in milligrams. On this end, decagrams, hectograms, and kilograms. Kilograms, I'll bet if you've ever had a science class, you have heard this phrase before in the United States. We shouldn't make that decision, is really, not to digress, but a person should be trained to think scientifically, just as they should be trained to be an artist. Everybody's capable, right? So don't make them as separate categories of people. That's not right. Teach your kids to be mentally flexible, right? Use this everywhere, right? This is where you're starting, which again coincidentally is the base unit, so it's just going to be in the center here. And this is where you're going. So if you're going from grams to, pardon me, centigrams, it's 2 jumps. Right? Which direction? Towards the right in this case. So you take your figure 14, and remember that if it's a whole number 14, as it should be, the decimal would be there to start with. Right? Remember, decimal points are very often not written for convenience sake. But this is where it would be if you bothered to write it to start with. Now, if you're going to convert to a smaller unit, that would seem to amplify. All right? And the result will be you make 2 waves this way. So 1, 2, and just to exaggerate where it was, distinguish it from where it was to where it is going, the decimal point would be here. The reason for the waves is to be basically a pocket that you could fill in the necessary placeholders. So what is your amount? It's 1,400 centigrams. I know I was only going to discuss distances, but these are the base units, which is why it is imperative to bring it up. All right. So again, this would be somewhat misleading, right? You might go, hey, that's 14, this is 1,400, or 1,400. Why? Why is that so much larger? Because although you're talking about an unchanged amount of substance, a capacity, well, in this case, grams is mass, pardon me, you are choosing to use a tinier unit in order to express that quantity. This is, again, same amount, all right, just smaller unit. So it looks like it's something quite large. It's misleading, right? You think of 1,400 as being large. You have to sort of break with the sort of brainwashing we're used to, the conditioning. This is expressing a mid-size unit in a larger unit. This is expressing a mid-size unit in a smaller unit. And this is the effect. All right. Again, it is the same thing as if you multiply by 100, essentially. A centimeter, there are 100 centimeters in 1 meter. Right? So this would be the same relationship between grams and centigrams. You would multiply by 100. But without dwelling upon that, you can convert to it very easily. Most people don't bother to think of it that way. All right. Let's do an extreme. All right, suppose you suppose you had 80 kilometers and you were converting it to centimeters. Right. If, again, you are, this is distance we're back to, converting between units, metric units, draw a table just to get used to it. Eventually, if you do these enough times, you don't need the table anymore, but this is to get your feet wet. You would have decimeters this way, centimeters, and millimeters. Good to know the abbreviations, of course. And then on this side, decameters, hectometers, and kilometers, kilometers. All right, now, remember, this is what you were given, so this is where you're gonna start, and this is where you're going. So, km, kilometers, you would be here, and centimeters is over here, x. So, how many spaces is that? Count the increments in leaps. 1, 2, 3, 4, 5. 5 jumps. Right. Again, it's intuitive on the horizontal scale because it tells you which way to move the decimal point. That's kind of cool, right? So here you have 80, and the decimal point would start here. But since, again, you were headed in this direction, make 5 waves that way. Right. 1, 2, 3, 4, 5. And fill in the pockets with placeholder zeros. So 0, 0, 0, 0, 0. Right. Now, if you're being a good American, again, because we're talking about a very large whole number, we would put a comma there and also there. So let me just rewrite this a little bit nicer and neater. In the United States, we would write it like that. 8 million. 8 million centimeters is the equivalent of just 80 kilometers. Well, 8 kilometers is quite a long distance, actually. But if you chose to use a much smaller unit to express that distance, look how large a magnitude of figure you would have here. Right? It still represents the exact same physical distance, it's just using a small unit to talk about it. Right, 8 million centimeters. Okay. Okay. Once you get acclimated, what you do is compare things. So just remember, when we compare, there's 2 ways to do it. You could order things from least to greatest. Or in theory, you can order greatest to least. I don't know why I'm writing capital letters here, not there. Usually what is sufficient is you separate things by commas. When you're comparing, when you're listing, right? But you can also use the less than and greater than symbol. Right? Least to greatest would have you orient the symbols this way. Something is less than something is less than something. Right? The smallest thing would be on the very far left. If you choose to arrange things in greatest to least, greatest to least, elitist is not a word, least, right? Then you would orient it like this, greater, greater, and so forth. You know, something is greater than something else, which is greater than something else. I think probably when you're doing your homework in my lab, they're probably content with just the commas, but this is, I think, in a more elegant way of writing, just my opinion. All right, so let's do this as an example. If you were to order from smallest to largest length, these figures, 3.4 meters, 3,421 millimeters, and 104 centimeters. Right. Notice that you can't really make a comparison immediately because you have different units. Remember, now that's a nice green today. Remember, to compare must be the same units. It's not a fair comparison. And so you could, change them into one consistent unit. Now, unless they specify, you can do whatever is intuitive to you. You can make them all meters. Or you can make them all centimeters, you can make them all millimeters, whichever you really prefer. It's the order of which the figures should be, from smallest to largest, that is important. So let's do this maybe in 3 parts. If we are given 3.4 meters, 3421 millimeters, and 104 centimeters. Let's just make them all meters. That means that this one you don't have to touch, just leave it alone, right? That's 3.4 meters. Right? How many meters would this be? How many meters would this be? In this instance, you're always going to get stuck doing 2. Again, if you're not familiar, draw the scale. A meter would be in the middle, decimeter, centimeter, millimeter, and decameter, hectometer, and kilometer would be here. And I'll just do the same thing really quickly here. DM, CM, MM, DAM, HM, KM. Okay. Millimeters is what you're starting with, so you would put a dot here. Right? And if we've arbitrarily chosen to convert to meters for the sake of comparison, then we would convert from here 1, 2, 3 spaces. And we would take the number 3421, decimal there to start with, and make 3 decimal moves here. Jumps 1, 2, 3. Which would make this 3.421 meters. 100, centimeters, a little bit further over, would start here. Converting to meters, you've got 1, 2 spaces. Okay, and so if you have 104, the decimal would begin there, and you just make 2 jumps, 1, 2, and you end up with this, 1.04 meters. All right, now, I'm going to write the equivalent of these two immediately underneath them. 3.421 meters. 1.04 meters. If it makes you feel more comfortable, and I wouldn't blame you, now that you have everything converted to the same unit, you can, if you want to, make them the same width, so to speak. Like for example, this is 4 digits wide, right? And 3 from the decimal place. So you could make this the equivalent of that just by inserting some placeholder zeros. That might make it a little bit easier to read. So that would make this 3.400 meters. And the same thing over here. 1.04, we could stick another 0 in here, placeholder, it's not going to hurt it, right? So it's a little bit easier of a comparison now, right? Because it's like comparing 3,400 to 3,421 to 1,040. Which of those would be, arguably the smallest, right? This one. So that will go first if we're specifying that it must be from smallest to largest, from least to greatest. So in black, maybe I'll do that right here. Well, just for the sake of space. Let me write this in the middle here. Okay. The smallest is 1.040. So I'll use the original figure, 104 centimeters. And then the next one would be 3.4 meters using the original figure. And then the next one would be 3,421 millimeters. And again, if you want to be very fancy, use the less than symbol. It would be oriented like that for least to greatest, smallest to largest. So in lieu of a comma, you could say, well, this is smaller than that, but this is smaller than that. Right. That's somewhat fancier. Anyhow, this would be the appropriate order as it is specified, smallest to largest. 104, 3.4, and 3,421 with their respective units, centimeters, meters, and millimeters. Okay? All right. I think that is it. For today, let me just check. Yep, okay. All right, let me stop here. As I mentioned, we're only going into really distances today. So we've introduced metric system conversions between units and just the one-dimensional units. Okay, all right. If you are following along, not to berate any of you, we're about the halfway point in the summer session, right? So if you're a little behind, you probably want to catch up at this point, okay? Don't let it hang for too long, especially when we get to the chapter 12 material, which is maybe alien, right? Statistics, maybe the first time you've seen it. You don't want to wait until the last second to start doing the easier stuff. So do section 7.1 in my lab, also the prereq, if there's a prereq, I believe there is. I gotta check. And then you are where we're supposed to be, right? Again, midpoint of the semester, so to speak, session. So try to catch up if you haven't done the chapter 6 or chapter 4 material yet, okay? This is the current assignment, okay? All right, thank you guys. I'll see you again tomorrow. Be careful out there.